Good morning and welcome to the 23rd annual exhibit of hydrogen and fuel cell technologies. We've been here for quite some time talking about innovations, growth prospects. We also know there are hindrances. One of the hindrances, of course, is we have no hydrogen grid. We have no conventional way of transporting large quantities of renewable energy from the north of Germany to the south. And this is really limiting our commercialization of these technologies and the expansion, of course, of renewable energies. So these are large issues, and we need solutions. I'll be talking to Dr. Cornelius van der Heydt, who's Head of Business Development at Hydrogenious Technologies, and he's going to tell us about how to transport and distribute hydrogen using liquid organic hydrogen carriers. Please welcome with me Dr. Cornelius van der Heydt.
Hey, nice to meet you.
Good morning. First and foremost, of course, we should hear something about the company Hydrogenious, when it was founded and where you're located and what you do.
And what we do, yeah. So Hydrogenious Technologies is a startup company founded in 2013 as a spin-off of the University of Erlangen, Nuremberg in northern Bavaria. And we specialize on the technology that you mentioned, on liquid organic hydrogen carriers, which is basically a technology to chemically bind hydrogen to an oil, to a carrier oil, which has significant advantages in transport, storage, and handling of hydrogen in general. We are 45 people by now, and yeah, are doing our best to closing that missing link of hydrogen storage and transport that currently exists.
Of course, this is the main focus of our talk here, and we're going to get to the applications. But first, the core technology, you get a little bottle here, and that illustrates how easy it is to carry. You're allowed to bring it in the building. Yeah. That's phenomenal as well. So what is that?
Yeah, so basically that's the oil that we use. It's a standard product from industry, a thermal heat oil for high temperature transport. And what we do is we chemically bind the hydrogen to this carrier oil. The oil itself is hardly toxic, is hardly flammable, non-explosive, and the storage density, now that includes hydrogen here, and the storage density is actually comparable to storage at over 2,000 bar pressure. So if you open a 2,000 bar bottle, you can imagine what what would happen. And this, yeah, exactly. And this liquid is...
It would blow us away.
Definitely. And this liquid is, for example, not classified as dangerous good according to ADR and all the other transport regulations that you have, making transport on trucks, on trains, wherever you want it, even in planes, very, very easy. And to be honest, I sometimes send this in a canister with DHL to other universities or something, and they say it's fine.
Okay. So, die Deutsche Post weiß es nicht. Okay, so the German postal system doesn't know. What they don't know can't hurt them.
That's true.
Okay, of course, it's a reversible process. Yeah. You need a source of hydrogen, and of course, electrolysis is producing large quantities. In fact, the electrolysis industry is waiting for methods of transporting stuff. Let's compare this technology. We know that there's other reversible storage processes. I think of metal hydrides as the obvious comparison. That is, you put hydrogen into a bottle with metal hydrides, you store it, and then in order to extract that, you add a little bit of heat, and out it comes again. So, yeah, how would you compare your technology with metal hydrides? What's the advantage?
So, you're absolutely right. The basic concept is the same. We put hydrogen in, coming out of an electrolyzer, and when you walk around here, you see that basically all of the electrolyzer companies now promote concepts with 50 megawatt electrolyzers, 100 megawatt electrolyzers. I haven't seen a metal hydride system in that scale. That's because metal hydrides are either very, very expensive in the storage substance, if they have high storage properties or storage density, or they don't have a very high storage density, which doesn't really make them suitable for road transport. And now we kind of combine both. We have a liquid, which is very cheap. It's below €5 per kilogram. Which has a storage density of, in gravimetric terms, of 6.23 weight%, which is, the DOE once gave the target of 6 weight%, so we actually outbeat that. And you're dealing with an oil, and human beings are used to dealing with liquids. We just from a gut feeling, basically, we have the feeling that we can handle liquids easier than gases, for example.
Whenever we get to the debate about efficiency and cost, I always have to sort of take a step back and say, well, efficiency doesn't matter sometimes if you have renewable resources that you're not harvesting. If you have biomass, it's a free substance. And if you're 70 or 80% efficiency, of course, it's nice to be more efficient, but there are efficiency issues and there are cost issues. And of course, these are all comparative right now. How do you break down the numbers of efficiency and cost?
So in our system, you have to divide or differentiate between 3 steps, basically. One is the storage step, which is a hydrogenation process, a catalytic hydrogenation process. And when you have a PEM electrolyzer, where the hydrogen comes out at 25, 30, maybe 50 bar, that's exactly the pressure we need. So we don't need any compressor, we don't need any other system, basically, except for our hydrogenation system. And you can go directly into the oil. So there's no efficiency loss there. And then where today the biggest loss in efficiency actually comes from in transport is the low storage densities when you transport hydrogen on a truck. So today standard is something around 250 bar. That means 350 kilograms of hydrogen on a tube trailer. There is 500 bar now, but compressing up to 500 bar does need a lot of energy. And then you still only get somewhere between 600 and 1,000 kilograms of hydrogen on a tube trailer. And the factor of cost, that tube trailer costs you several €100,000. Now, what we do is we use a normal fossil fuel trailer, basically. We get up to 1,800 kilograms on that trailer. You can even use a train, which makes it even easier, because how much oil do you get on a train? That is then converts to several thousand kilograms of hydrogen. And then you can actually distribute that hydrogen in the oil to wherever you need it, to different refueling stations, industry customers, and so on. And there you need to extract it, which again is a catalytic process where we need to insert heat, and the exact same amount of heat that we need to insert there, we actually have as an exothermic reaction at the storage process. So ideally we use that heat as well. But then that's kind of the only efficiency loss we have in the whole system is the heat we need in the end. And with industrial processes, you can use waste heat at a refueling station. You can either use electricity, which is a green, hopefully available as green electricity as well. So overall, the cost of our technology is significantly lower than the overall cost to the customer of conventional technologies. So I don't think it's, as you say, all about efficiencies, it's mainly about cost.
Cost is, of course, supremely important. It's always the struggle to deal with this wonderful energy carrier that has lousy energy density. And we're always trying to crunch those numbers and improve things. We all know that 700 bar tanks, which used to be featured here at the stand, have a loss of around 30% of energy just because you're pumping them up. So these are issues. There's another issue, though, of course. Hydrogen is a valuable gas, and one of the reasons it's so valuable is because the PEM cell is wonderfully efficient at converting that back to energy, and the whole cycle is what we're working towards. You're sort of the mediator of this cycle, but it's the production of hydrogen because we don't have any technologies to store renewable energies in these volumes. So we got to store it, and then we have to transport it, and then on the other side we have the PEM cell, which is a wonderful technology to get a maximum amount of energy back from that cycle. That's relatively efficient. PEM cells, though, they really, really are fussy when it comes to purity. That is, if you're, mixing this up with oil, dumping it in there, it already sounds nasty to me, and then you want to get the hydrogen back out again. Cell poisoning is like a huge danger because PEM cells are also expensive technologies. If they're run clean, they run for a long time. If there's any impurities in this stuff, how pure are you?
Well, we operate a PEM fuel cell with the hydrogen that we release, so I think that's the best proof that we actually say, connected. There's a general logic to it. Our release process is a catalytic process with a platinum catalyst. And so we don't like those catalyst poisons either. So we don't have carbon monoxide, sulfur, chlorine, or whatever in the system, because if we had that in the system, it would actually harm our own system. So there is no none of those poisons for the fuel cell are actually in the system. And what makes it very easy to purify the hydrogen when it comes out from our liquid is a boiling point difference of over 600 degrees centigrade. So that this liquid actually has a boiling point of roughly 390 degrees centigrade. And hydrogen is where? Somewhere minus 253 degrees. So just condensing out possible impurities is very, very easy, because what can be in there as impurity is maybe some spots of this liquid, but that's easy to condense out.
Mm-hmm. Okay, so the PEM cells will be satisfied.
Absolutely.
You feed them what they need for their diet.
Absolutely.
When we talk about distribution, and if this is the magic of the technology, we want to use the liquid organic hydrogen carrier to supply, for instance, the automotive market, which is already interested in buying this expensive resource at a price that makes the whole system worthwhile. But this means you really, optimally, you want to start distributing at, for instance, tank stations. You want to get the buses running. These dudes that run these stations, they're interested in safety, for instance. I mean, if you install this and you have your system which changes the temperature and extracts the hydrogen, just how safe is this whole process? Can you smoke a cigarette next to the how safe?
You could without a problem. Actually, I've brought a video because we've taken our engineers and I told them, well, does it burn? And that kind of what happens when you put an engineer to, can you see? Yeah. When you put an engineer to, to test something. So we had our little kitchen set up and got some torturing instruments. So here, what is maybe quite interesting to see as well is the plastic IBC. That's how we store hydrogen. That's 57 kilograms of hydrogen in there. And as you can see, it's just, decanting wine, basically. So that's the carrier oil that we use. Once the orange yellowish liquid is without hydrogen, so that's unloaded. There's also always a change in color, so it's quite easy to identify. And now that's our torturing methods. And I would not recommend to do that with pure hydrogen. So, what you can see on that's the orange again, that's without hydrogen, and now we actually have now it comes even worse for the liquid. And as you can see, the liquid, even though it's, I don't know what that flame has as a temperature, several hundred degrees centigrade, actually doesn't start burning. And so that's the safe it is, definitely.
So this is a lesson on what engineers do when you leave them alone in the lab.
Yeah, definitely.
But it's also very informative because, in fact, when you think about safety issues here, what's safer, a tank full of gasoline or a tank full of the liquid organic hydrogen carrier?
The carrier, definitely. It's less toxic. It's not classified as a hazardous good. Normal gasoline is. It's hardly flammable. Yeah, you can't drink it, okay, but it doesn't burn. So definitely the carrier.
So even a spill would be less dangerous if it's that.
Even a spill is less dangerous, and it's very easy to collect it. It's not fish toxic or something. So.
Of course, when we talk about distribution, we're also interested in the way things operate on the ground. Sometimes this industry doesn't really look into the commercialization process from the perspective of those who ultimately will sell the goods. And we're talking about conventional tank stations. They have limited space and they don't want a huge footprint. So having a pile of tanks with huge volumes is really an issue. Energy density here is like a fascinating thing. So it's all about conventional handling. Is it going to be something new for them to do? And how small the actual pump on the ground can get in order to tank up these vehicles. And of course, the cost of all that system. So let's talk about the footprint.
So the biggest advantage is you can actually continue using the existing infrastructure at a refueling station. So all the gasoline and diesel tanks, you just clean them out once, leave them underground, and can use them for the carrier. So that the footprint is not really an issue. If you have pressure tanks at the refueling station, today, that is maybe not an issue because we're talking about 100 kilograms of hydrogen or something, but think about a grown-up refueling station where we talk about supplying a refueling station with one of those 50 megawatt electrolyzers. That's 30 tons of hydrogen, you'll probably store something like 3, 4, 5 tons of hydrogen at a station. That does require either footprint. It's a safety issue if you store it in molecular form, and with a carrier liquid, use the existing infrastructure, use the existing tanks to deliver the hydrogen. You can pump it into the tanks. It's very easy in handling. So that's what people are used to.
I should add that if we do have a minute or two for questions from the audience. If there are any questions, I see there is.
The oil you use for this recycling process, does it alter or can you use it endlessly?
Well, nothing really is endless, but you can use it for 500 to 1,000 cycles. So the cycle stability is very, very high. And if you don't do anything, then it actually has basically a non-ending shelf life. So it's not degrading just over time as well.
Are there any other questions? Right.
Hi, I'm sorry, I may have missed the density part. So how much hydrogen do you actually store in a liter or a kilogram of the liquid?
Yeah, in 1 cubic meter we can store 57 kilograms of hydrogen. So.
And of course, to break it down to a very objective example here, how much hydrogen is in that?
So that's, what is it, roughly 50 milliliters. That is, now who can do the math? It's a bit, 50 milliliters is then probably something like 200 liters. Is that roughly right?
Sounds good to me.
Factor in volume, it's a factor of 1 to 630. So norm liters. So you better do the math.
We'll get our calculators out after the break. Is there any other question from the audience? Why this is fascinating, I want to get to the big issue, of course. I've already mentioned that there's a huge source of renewable energy that is just waiting to be harvested, and what's blocking it is that we don't know how to get, for example, a lot of this wind turbine-generated energy from the north to the south, where it's needed. And of course, being as we are in Germany, there's a great debate about how to do that. One of the solutions potentially is to run high voltage cabling from the north to the south. And you know how that is, not in my backyard, I don't want it in my neighborhood. And they're still debating about this, people don't know. We have a number cruncher over here from Jülich. What he suggested is what we really need to do is run a hydrogen pipeline from the north to the south. That is electrolysis close to where the wind turbines are, and then running that hydrogen. He said that's far more viable than creating the cabling system. And that may be true, but the thing is, we're still waiting for that hydrogen pipeline.
And has he calculated what that would cost as initial upfront investment?
This is the thing. The initial upfront investment is so large that we're going to wait a long time. We're going to be generating a lot of carbon pollution, and this is why we're really looking for a solution where the entrance cost is low. So how does your technology play into that debate?
Exactly, that's from my perspective as well, one of the main points. I mean, a pipeline, yes, is a great idea if you have huge volumes, if you have a continuous demand for hydrogen. That's why in all the refineries and so on, they use a pipeline on site. But as I said, we can't really wait for that. And we can use trains, for example. There is railways going from Hamburg to Munich. That's not an issue. You can use, and today they transport oil and chemicals and so on in that way. And we can actually transport huge amounts of hydrogen on a train from northern Germany to southern Germany, where we don't have any wind. We are located in Bavaria, so we'd be the first ones to profit from it. So we basically enable using an existing infrastructure without the need to install a new infrastructure, which does require huge upfront investments. So I think we shouldn't wait another 20 years or something, but use something that works now.
And this is where the math has to be done again, of course, because if you look at a typical train car with a tank on it, and you compare the number of kilowatt hours of compressed hydrogen with the number of kilowatt hours of the liquid you produce.
So it is roughly a five-fold increase. So we get up to 1,800 kilograms. That is, in kilowatt hours, roughly bit over 50 megawatt hours on one trailer. And as I already mentioned, standard on a tube trailer today, 250 bar is something like 350 kilograms, which is a fifth of that. But at 250 bar, and even 250 bar can be handled in an industrial setting, but not as soon as you go into public, where we have a refueling station in those. And when it comes to very large numbers, I've done the math yesterday, so I hope I remember it. If you take a 50 megawatt electrolyzer, which is rather one of the smaller ones that's been promoted here, and you run it for 24 hours, you get nearly 30 tons of hydrogen. Now, 30 tons of hydrogen, that's, depending on which pressure technology you use, something between 30 and 80 trucks per day, compressed to up to 500 bar. That is a lot of infrastructure, and that is a lot of hassle for the logistics people. And with our technology, you need something between 15 and 20 trucks, which is still 20 trucks a day, okay. But it's ambient conditions. You can just pump it, and the infrastructure is there.
And of course, trains instead of trucks are
trains are even more efficient, definitely.
We at the hydrogen and fuel cell industry, we have an allergy against trucks because, of course, all the demonstrations historically, if I go back 17 years, you look at the purity, you generate hydrogen, then you use it in a hydrogen vehicle, and of course, the demonstration products often had a trucking into a location that was remote, a bit of hydrogen fueling up that thing and driving back, and someone always sits down and does the math and says, this is a horrible equation. But the entrance technology is really the key here, and I think you've got a wonderful solution, and we need to follow this. So we should keep the conversation going. Your booth is right around the corner here.
B74, right around the corner here, and more than welcome. My colleagues and me will be there all day and all of tomorrow. So if you have any questions, just come and visit us.
Yeah, wonderful. I've been talking to Dr. Cornelius van der Heydt, who's head of business development at Hydrogenious, B74. It's been a fascinating conversation. I hope to see you back here next year with progress, because we need progress.
So do we. Thank you very much.
Thank you.
Thank you. Bye-bye.
And thank you. We'll be back in a minute with another conversation. We'll be talking to Dr. Heinrich Lungenkranz, who's from Impact Coatings, and they'll be talking about production lines for bipolar plates to China. Stay tuned. The drinks are on the house. Back in a minute.